Okay, this is Chapter 3, Motion in 2 or 3 Dimensions. And what we're really going to do is we're just going to extend everything that we've learned about kinematics into 3 dimensions. We're going to use vectors to represent the position of the body, not just in the x or the y dimensions alone, but in the x, y, and z dimensions. And the definition of velocity is surprisingly similar to what we learned for 1 dimension. Talking about kinematics, we have to talk about accelerations again, now not just in 1 dimension or 2 dimension, but now in 3 dimensions. We can describe a projectile that's thrown in 3 dimensions in this chapter. We're going to talk very briefly about circular motion. We're going to come back to that in a couple of chapters. And lastly, we're going to talk about reference frames, what it means to have a velocity in a reference frame that might be different than your own. So some of the questions that we'll be able to answer by the end of this chapter would be, where would a batted baseball land? It's going to follow a projectile. So we're asking ourselves, okay, where does it land? But maybe not just in x space, but maybe in x space and z space. If a cyclist is coming around a curve, much like these fellas down here, and we'll say that they have a constant speed, is he accelerating? And we'll talk about reference frames and how maybe having a moving observer might change our reference frames. And all of this we're extending our description of kinematics to 2 or 3 dimensions. Now, previously when we talked about an object's position, we had a reference frame and we said, an object's position is going to be, x2 minus x1, and we have some position vector that might look like that. To do this in 3 dimensions, we want to talk about those unit vectors that we talked about in the first class, I hat, j hat, and k hat. And what we're going to do is we're going to describe a vector using unit vectors. So if we have our y-axis on top, our x-axis over here, and now we're introducing the 3rd dimension, z, then we define the unit vector I hat to be along the x-axis, and if we travel some distance x along our x-axis, then we say that we've traveled x I hat in that direction. That's our position in the x. That's our position in the x. And then using the tail to tip method, suppose we go up in the y direction by y j hat. Now the unit vector is described by the j, and how far you traveled along that direction, along the j hat or the y direction, is described by the number, in this case y. And bringing it into 3 dimensions, now suppose we travel in the z direction, we would describe our position vector in that direction by zk hat, and our resultant vector is going to be defined from the origin, and it's going to point up in 3 dimensions. You can kind of picture the box here. So up to the right and a little bit towards you. And we would define the resultant vector using the tail to tip method right down here, where again the x, the y, and the z are now numbers in the multiplied by the 1 unit vector in each direction. Now, we talked about the average velocity last time to be the change in position divided by the change in time, and now we're simply saying that this position just doesn't have to be in 1 direction. So suppose we're talking about 2 positions, P1 and P2, and we can describe these by the 2 vectors R1 and R2. then the change in r, how much the position vector has changed, is described by that vector right there. And now we simply define our average velocity to be how much r changed as a function of time. And simply r now is not just in one direction, it's in multiple directions. Now, the instantaneous velocity we defined last time to be the Vx is equal to the derivative of x with respect to y, right, with respect to time. We can now look at the components of the instantaneous velocity in 3 dimensions, and we're just taking a look in the xy plane right here, where we have some particle that is moving in that direction, and we say we know that the instantaneous velocity is simply the slope of that guy right there. And now simply the motion just doesn't have to be in the x direction, it can be in the x direction, and the y direction, and the z direction, and we take our derivative with respect to each one of those position variables independently to get the instantaneous components of the velocity. And simply noting that these are all derivatives, so the instantaneous velocity is always going to be tangent to the path. We could draw a similar plot for this particle, maybe now not in the xy plane as we are here, but we could also look at this in, say, the xz plane, and then we could see how the particle might be moving in that direction and take an instantaneous velocity in that direction as well. Okay, average acceleration is very similar to what we already know about acceleration. We say that the average acceleration is the change in velocity as a function of time. And now we're not necessarily talking about one direction, we're talking about velocities that could be in more than one direction. For example, if we consider 2 points along a curve, point 1 and point 2, a car is going to have some velocity as it rounds a curve, and it's actually going to be tangential to that curve. That's its velocity at point 1, v1. At point 2, the car is also going to have a velocity tangential to its motion, and we're going to say that's its velocity at that point. Now clearly you can see that the two vectors are of different lengths, and so that would tell you, yes, the car definitely changed its velocity. However, if these two lengths if they happen to be the same, v2 is equal to v1, and the bars right here just indicates magnitude, so it would be the speed. So if the speed at v2 is equal to the speed at v1, the vectors would be the same length, but the velocity would still have changed because, or the car still accelerated because the velocity changed not in magnitude but in direction. So thinking back to the BMX bikes rounding the curve on the slide with all the questions on there, if you have a constant speed and you change your direction, you have accelerated. Now the book does this graphically, where they take v2 and they take v1 and they say, what is v2 minus v1? So if I have my my vector v2 right here, not quite the same length as the book, but I'm trying. Now if I were to add v1, then I would put v1 right at the tip of v2, and I would add that right there. However, when I'm subtracting a vector, remember I am actually adding the negative vector. So this would be negative v1. Doing that would be wrong. And so this right here, this vector right there, would be my delta v. and the book does that right there. So you can see that the change in velocity is inward to the path, and the acceleration is the change in the velocity with respect to time. So you divide by time, you might get a slightly different length acceleration, but it's in the same direction. It's inward towards the curved path. Now, the instantaneous acceleration is exactly what you would think. Last time we defined it to be the acceleration was instantaneous acceleration was the change in x with respect to time. Now we're just simply talking about three dimensions, and we can write this much like we did with the velocity as the acceleration in the x direction, the acceleration in the y direction, and the acceleration in the z direction. And you can be accelerating in one, two, or all three of these at once. And reiterating what I mentioned on the last slide, any particle that's on a curved path, it is accelerating even if it has a constant speed. So thinking back to our example from the last page, if we wanted to find the instantaneous acceleration, then what we do is we consider the limit as delta t approaches 0 of change in velocity over the change in time. So rather than looking at this big long time interval, we simply look at smaller and smaller time intervals until we're looking at a very, very, very small time interval, and the instantaneous acceleration is calculated at that one single point. And again, it always points inward on a curved path because you want your velocity to change in that direction. Now, with straight line acceleration, it's exactly what we would expect. If our velocity is going in that direction, and at some point too, it's also going in that direction as well, but it's a lot longer, we know that it has accelerated, and so we know that there's some acceleration in that direction, simply because the velocity vector has increased in length. Now, if we were to consider an object moving on the curved path, again, I've said that it is accelerating. If it doesn't change its velocity, if it's, say, going around a circle in a constant speed would mean that the length of the velocity vector is the same anywhere in that circle. Now, if any component of this acceleration is in the direction of the velocity, then it must change the length of that velocity vector. It must also change the speed. So for it to have perfectly circular motion, the acceleration vector in a circle must point inwards directly towards the center of the circle. When it says the acceleration is normal to the path, what it means is it is perpendicular to the path of motion. Now, if I consider over here the case where the speed is increasing, and this right here is the the center of the circle, if I want my velocity to increase over time, then some component of this velocity vector, or of this acceleration vector, must point in the same direction as the velocity. That will make the velocity vector longer in that direction. Similarly, if the velocity vector gets shorter at the next instant, then some component of the acceleration vector is going to point in the opposite direction of the velocity. That's going to slow it down.